Okay, yeah, so let's take a look here and tell me what's not good about their solution.
They didn't take a T out of the
Yeah,
bottom.
they didn't, right? They didn't. So we could go from there. I mean, it's always good practice. So what could we do with that bottom quantity? Everybody take a look up here and focus up here, just to make sure you get this, because this is a good thing to remember how to do.
Take it.
Okay, so inside the t to the quantity to the fifth, right? I could write that on the bottom as t times the quantity t squared minus 6 all to the fifth, and then split that up, right, into a t to the fifth times a t squared minus 6 to the fifth, okay? And so really, what they probably should have gotten, but maybe they're marking it wrong if you write it this way, and that would be a problem on their part. Has anybody gotten this one right?
If you write it out all just in expanded form with like 8 million parentheses, as long as you have the right numbers, they'll tell you it's right.
Really?
Yeah,
Okay,
no
so they're not.
way.
You
You've
can
been doing this?
You can come look and see what I got, but it's not like that.
Okay.
And I got
Okay.
it right.
I was just wondering if that was maybe it, because then, like, really, we should be able to cancel a t to the eighth with a t to the fifth and get a t cubed on top, right? So the simplest answer really should be -4 t cubed, t squared plus 6.
Well, then you have a T squared. Oh, never mind.
Minus 6.
Yeah, it's minus 6. I thought it was.
We should have that, right? That should be the simplest answer. Okay. So it might be,
I think I just do wrong things on my way to get there.
okay. Okay.
Yeah, because the different times makes sense, like, mine definitely is.
Okay. Probably, maybe on this one, let's, okay, maybe the thing to do, let's go through number 8, and I was gonna do some log stuff today to help you, like one more log thing, but maybe I'll do that tomorrow and let you work and I can kind of go through this with small groups or individually. If we're having trouble and see we can catch the errors, okay? So we'll postpone things a day. What about, so this is, oops, hang on. So then, yeah, there's number 8, right? That's the one, the physics one? Okay, find the position, the particle's velocity and acceleration at t equals 5. So we have s of t, we have a position function, right? Here's our position function. Okay? How are we going to find the velocity?
Take the derivative.
We're going to take the derivative. Okay, so now I want to think of this, when I'm using my chain rule, how am I going to rewrite that, or at least in my head?
You're gonna put it to the negative.
1/2. Okay, good. So we had 16 plus 4t to the 1/2. So then s prime of t is v of t, and what's that going to be? We're going to have outer layer, I've got hand to the 1/2. So the derivative of hand to the 1/2 is going to be 1/2 hand to the minus 1/2, good, times the derivative of hand, which is 4, okay? And so the 4 and the 1/2 make a 2, and I just get 2 times 16 plus 4t to the negative 1/2, right? Now if I want to write that as a radical, just for purposes of evaluation, we probably want to leave it like this to take our next derivative, don't we? Right? But for purposes of evaluating it, maybe we want to write that as 2 divided by the square root of 16 plus 4t, right? Okay, so we could do part A then. If we evaluate the velocity at 5 seconds, v of 5, this is going to equal 2 over the square root of 16 plus 20, square root of 36, what's that? 6, good, so I'm gonna get 2/6, which is 1/3. Okay, and whatever units we're using. They even tell us, yeah, meters, so meters per second. Okay, so now we wanna do acceleration, so we'll use this. That's the most convenient place to continue differentiating, where it's written as a power. So A of t is gonna equal d prime of t. So what's that gonna be? See what I got? So -1/2 times 2 would just be a -1, right? I get negative hand to the, what power? -3/2. We gotta subtract 1, right, from the power, from the exponent. So -1/2 minus 1 would be -3/2. And then the derivative of hand is 4. Okay, so when I write that, I could write that as like a radical on the bottom. That's gonna look like a -4 on the top, and on the bottom I'm gonna have a 16 plus 4t to the 3/2, right? And we want to evaluate that at 5, don't we? So A of 5 equals -4/36 to the 3/2. So 36 to the 3/2. How do I deal with that? So I square root it and then cube it, right? Okay. So the square root of 36 is 6. Cubed is 216. So we end up with -4/216, which I can reduce to, what is that, 1/108, so 108, so 54. Right, so we just reduce that fraction, okay? And that's gonna be in terms of meters per second squared, right? We're using meters and seconds. Make sense? Okay?
So, once we go from velocity to acceleration, did you go back to that? Yeah, okay. That's what
We want to, this should be easier to differentiate,
Mhm.
right? So
Yeah.
we'd rather use, we don't want to use,
So then.
writing as a fraction is really inconvenient,
Mhm.
right?
So then, I guess I'm wondering where the -3/2 came from.
Okay, because of that's our power rule. The derivative of hand to the
okay.
-1/2 is -1/2 hand to the -3/2.
Perfect, thank you.
Mm-hmm.
Use number 7.
Okay. Did I forget? Oh, no, it was that was right, 2 canceled. Yeah, number 7. Okay, so, get there. Oh, yeah, this is pretty good. We'll talk about this one. Okay, I'll get this one captured for us to look at. Okay, so this is a pretty good question. This is one that, honestly, this one, something like this sometimes shows up as the super hard problem on the AP test for the open-ended questions on the AP test. But it's not that bad. The graph in the accompanying figure shows the average Fahrenheit temperature in a city during a typical 365-day year. The equation, so here's the equation right here. It looks really complicated, right? We get this trig function. Approximates the temperature on day X and is graphed in the accompanying figures. Okay, and it makes sense. So where's probably summer? You know,
July.
yeah, well, that makes sense, doesn't it? Summer's in here where it's the hottest, winter's over here where it's the coldest, right? Okay? So what do they want then? We want to know on what day is the temperature increasing the fastest?
I guessed in between March and May, but I didn't know the day.
Okay, this is at this point in the class, this is pretty challenging. How are we gonna go about this? What do you think? I mean, you can look at the graph, but,
So it'd be where the slope is like
The tangent.
okay, good. So we wanna know the,
Slope of the tangent line at the,
so what's this graphing? What's on X and what's on Y?
X is the days.
Days.
Okay, so X is the day, right?
Yeah.
And Y is
The temperature.
temperature. Okay, so then, what would a slope represent here?
What the temperature was on a day.
The change in
It's gonna be the change in the temperature with respect to the day, right? So it's gonna be the rate of change of temperature. Does that make sense?
Yeah.
Okay? So then if we're looking for the place where the rate of change of temperature is the biggest, right?
Yeah.
Okay? So what am I gonna do? How am I gonna find that?
Are you gonna take the derivative of your equation, so then you have the slope of the
Okay.
tangent line?
Good, if I were to calculate the derivative function, the value of the derivative is equal to the slope of the function, right? So the value of the derivative is gonna be the rate of change of the temperature, right? So we can do that. We can use our chain rule and we can do that. So this is Y. What's Y prime gonna be? By the chain rule. I've got my 34 out front. And then, what about the plus 25 at the end?
It just goes away.
That's gonna go away, right? So really, I just have to differentiate this sine function. Well, what's the derivative of sine hand? Cosine hand. So I get 34 cosine of hand. So that's just 2 pi over 365 times x minus 97, okay? What's the derivative of hand?
2 pi.
Do you see that? Right? Because I'm just gonna get 2 pi over 365 times the derivative of x minus 97, which is 1, right? So that's gonna be multiplied by 2 pi over 365. Okay, so if I want to write that, let's simplify that whole thing. So y prime equals 34 times that. So that's going to be, 68 pi over 365 times cosine of all this stuff. Right? If we're trying to find a place where the temperature is increasing the fastest, where's that gonna be? Where the derivative is what? But where, if I were to graph that function, it's gonna be where the derivative is. The derivative represents the rate of change of temperature, right? So where is the rate of change of temperature gonna be the biggest? At the max of the derivative, right? Does that make sense? Because that's what the derivative represents. So there's some good stuff going on in this problem, right? You've got to make that connection, that where the derivative function is going to be the biggest, that's going to be where the rate of change of temperature is the greatest. And doesn't that just mean rate of change of temperature is the greatest, means the temperature is increasing the fastest, right?
Yeah.
Okay? So if I were to graph this cosine function then, what am I gonna get? Well, let's graph it and see. Right, if we look at a graph, and then we'll come back and we'll do the algebra afterwards, but if I graph this on Desmos, okay, so what do we get? 68 pi divided by 365
The question how
cosine 2 pi.
No, I just.
Okay,
yeah.
there it is. Now we need to probably change our scale pretty massively here, right? So we want to go from where to where? 0 to 365.
You were really close.
By, I don't know, 50s.
Sure.
Okay.
Can we do 31 just for months?
What now?
Like steps of like 30 or 31.
Oh,
for like
yeah, yeah, that's a good idea. Sure.
I thought you were saying it was
Okay,
30
that's
months.
good.
No, no.
And then y should probably go from where to where? It maxes out at 68 pi over 365. So what's that going to be? About a little less than 1. So we'll just go from -1 to 1. Okay, there's our graph. So where do you think this thing is going to be a maximum?
Right past 90.
Yeah, in fact, if I click on this thing, oh, what do you know? How about that? But why should it be that? I mean, think about, this is just unit circle stuff, yet again. We always go back to the unit circle, don't we? All right, so let me take a picture of this. That's a pretty good looking graph. Let me get a picture of that. What? Yeah.
So it's gonna be. If I get this right down.
It's just the number.
Are you kidding?
Why am I like so upset but so happy by whatever?
That's what it's stupid.
It's gonna
The
be.
number in front.
Okay, so that makes sense, doesn't it? That our point is going to be at 97. But now, how can we look at the trig function and see that?
Oh, in terms of.
If this is our derivative, think
This is
unit
stupid.
circle, right? Unit circle. Where is cosine going to be a maximum? Cosine is the x or y coordinate.
X.
Cosine is the x coordinate, right?
Mhm.
Okay. So where is it's going to be?
Power two.
It's going to be a maximum at pi over 2 or 0, right?
Yeah.
Okay. Right, makes sense. So then we want the argument when we're feeding the cosine function to be equal to 0, right?
Yeah.
Okay. Well, what's going to make that happen?
You just
Right. When is all this stuff right here? Right. This is like our theta. That's the angle that we're feeding the cosine. Right. Theta is going to equal 0 when all that stuff equals 0. Well, when does that expression inside? When does 2 pi over 365 times x minus 97 equals 0?
in
At 97, right? How about that? Okay. Make sense? Okay.
Wow. I struggled.
That's a tough one. I mean, that's a tough one.
And then
This one, I'll tell you what, this one is going to get a lot easier to do after we do optimization. After we do optimization, you could just say, oh, we'll just optimize that function, and you'll get the answer. So that was kind of a sneaky, tough, challenging one to give you right now. Okay? All right, did that help? I mean, does that make sense?
So what
That
about
makes
part
sense
two?
now.
Okay.
What about part two?
Okay, so part two,
You find the
what are you gonna do? Brittany, tell everybody. Everybody listen, please.
So you solve for the derivative,
Mhm.
and then it's the slope of the equation.
There you go. Yeah, so we're just gonna evaluate the derivative, right? So we know that the derivative is maximized at day 97. If we wanna figure out what is the value of the derivative, well, we just plug in 97. If we plug in 97, what are we gonna get? We're gonna get the cosine of 0 is 1 times 68 pi over 365. So the answer is 68 pi over 365, isn't it?
Uh-huh.
Right? That's gonna be the rate of change. Did we forget the 34 in there somewhere?
No, you times it by the 2 pi over 365.
Okay,
Yeah. It's there.
okay.
Okay.
I feel like I forgot that, because look, we have this piece at the end here.
No,
Yeah,
that was
it's
timed.
multi-
No, you timed it at the beginning. So
Oh, I got you. Never mind. Yeah, I see. All right.
You got it, you
I
got
could,
it.
it was behind that thing, I couldn't see it. Okay, we're good. We're good. Yep.
Are you gonna post the log assignment now?
Yes. I'll put it up